Hi, and welcome to the second exam for organic chemistry in fall of 18. This is version A of the exam that we're going to be working through first. Our first problem here, part A, we're going to give the approximate pKa value for each compound. We see water as our pKa standard of 16. This is hydronium next, as a pK of about 0. Acetic acid is 5. Ammonia is 35. And ammonium would be pK of 10. Those are simple memorization type problems. The next, we are looking for degrees of unsaturation. And in short, degrees of unsaturation is the total number of rings plus pi bonds that we see in the structure. And remember, pi bonds would be a double bond or a triple bond, where a triple bond is actually 2 pi bonds. So in our first example, we have 2 degrees of unsaturation from the alkene plus another 1 from the ring. So this gives us a total of 3 degrees of unsaturation. Our next example, we have a pi bond here. So that's 1, 2, 3, 4. So that's 4 pi bonds. Plus we have the ring system, which gives us a whole nother degree of unsaturation. So all of that gives us a degree of unsaturation being 5. Our next one here, we're just given a formula. So we need to compare this to the fully saturated version of that compound, and that's going to follow the formula CnH2n plus 2. So the fully saturated C4 compound would be 6 times 2 plus 2 being 14. We then take the difference of the fully saturated versus the actual compound given, and we see that the difference is 8 hydrogens. And if we divide that by 2, we get 4 degrees of unsaturation, or 4 pairs of hydrogens that are missing from the actual compound. And so that's our answer of 4. For our next compound, we see that it includes a bromine. So we need to not only find the fully saturated version of a C9 compound, but we also need to find what we're calling the hydrocarbon equivalent. So if the structure had hydrogens, all hydrogens instead of bromines, but the same number of degrees of unsaturation, how many hydrogens would it have? And so the rule for those is to add halogens to that. And since I'm going over the rules, I'll go for the next one too. We're going to subtract the number of nitrogens from the number of hydrogens, and we're going to ignore the number of oxygens. Okay, so going back to here, we're going to add the number of halogens to the number of hydrogens. So that's going to give us C9H16 plus 2. Or 18 in this case. So finally, we'll go back and compare it to the fully saturated form, C9H20. We see that we're missing only 1 pair of hydrogens, or 2 hydrogens total between 20 and 18. So the final answer that we get is just 1. That work for 1 degree of unsaturation. We'll follow the same strategy here. We have 6 carbons. And initially we have 5 hydrogens, but remember we're supposed to subtract the number of nitrogens from the 5 when we can ignore the number of oxygens. So it's actually a C6H4 compound. We compare that to the fully saturated C6H14 compound. This is a pretty big difference. We see it's a difference between 14 and 4. And we have 10 hydrogens missing, or 5 pairs, so we have 5 degrees of unsaturation. In part C, there are 2 different compounds here, 2 different names. We'll start by drawing the parent, 1,4-hexadiene. That's going to be 1, 2, 3, 4, 5, 6 carbons with a double bond on that starts on 1, and another double bond that starts on 4. And you're never too cool to number your carbons, to not number your carbons, 3, 4, 5, and 6. So let's add in the rest of the stuff. We're going to add in that 2,4 dimethyl group. So here's 1 on 2 and another on 4. And then finally, we're going to double check to make sure that this double bond on 4 is actually E. We can see here on this carbon, we're comparing a CH3 group to a carbon that's connected to another carbon and 2 hydrogens. So this is going to be what we refer to as the higher priority side. This is the high priority side of that double bond. And then on the other side, We see this carbon is connected to a CH3 group on one side and a hydrogen on the other. And so the CH3 group wins the high priority. Then we look across the plane defined by the double bond here, and we see that the high priorities are on the opposite side, so it is actually an E alkene as drawn. Great. Check. Let's go to the next one. We have 1,5-octadiene is our parent. 1, 2, 3, 4, 5, 6, 7, 8. Number those carbons. 2, 5, 6, 7, 8. We're going to put in all 2 double bonds. One of them starts on 1, the other one starts on 5. We have next, we have that 4 propyl group to add. 1, 2, 3 carbons total. We have 2 methyl groups to add. They're both on 3. And then last but not least, we want to make sure that that double bond on 5 is cis. You'll notice that there's no designation for the double bond that starts on 1. That's not isomerizable because it has 2 of the same atoms, in this case hydrogen, connected to 1 carbon, or in other words, it's symmetric. So we need to make this one actually cis. So we want this to be cis. Right now it's trans. So that presents a problem. Best thing to do is simply erase the smaller parts that are incorrect, meaning this 7-8 group, which I now apparently have to redraw. Oh, good. Just the 7-8 group needs to be removed, and we're going to put in its place the other hydrogen. So I redrew the components that were incorrect, meaning carbon 7 and 8 should be pointing up this way, and the hydrogens that I'm replacing it with, just to make it very clear, are shown there. And then finally, that was carbon 7, that's carbon 8, and this is now a cis double bond. Last but not least on this page, we're going to identify each functional group in each molecule and draw a dipole arrow for each polar bond. We have 2 alkenes on this molecule, right? This guy here and that guy there, those were both alkenes. I'm going to remove those arrows so they're not confused with others. And then on this molecule, we also have 2 ketones, specifically these guys here, the carbon-oxygen double bond, where they have carbons on either side of that carbonyl. So those are actually 2 ketones. And once again, I'm going to get rid of these notations so that they're not confused with dipole arrows. The main polar bonds are this carbon-oxygen bond here and here. Remember, carbon-carbon pi bonds are not particularly polar. I'll go back to the other functional groups. On this molecule here, we have a ketone. And this over here is specifically an ester. It's not a carboxylic acid, it's not an ether, it's its own very own thing. Once again, that's an ester. So let's find all of the polar bonds. Those are going to be, once again, the carbonyls. Carbon-oxygen double bonds are pretty polar. These are also being pulled away to that oxygen here. And I didn't leave a whole lot of space for it, and it's not a very polar bond, but you have all of those arrows going into that oxygen. So those are the functional groups and dipole arrows for those 2 examples, and that's page 1 for part A, for version A. Okay, bye.